Ladies and gentlemen, welcome to this session. One moment, please. Special session on innovative application for knowledge transfer support. My name is Sławomir Kłos, and I represent University of Zielona, Poland. It's in west part of Poland, not big university, but very fine. And we have today 3 presentations. It's a pity, but Justyna Patalas-Maliszewska could not come here, and we start from the second presentation, Metis, scalable natural language-based intelligent personal assistant for maritime services. Who will be present? Nikolaos?
Yes.
Gkanatsios. Okay, let's start. We have no limit time because we have only 3 presentations, but I think it will be good if we present the most important thesis of our work, scientific work, and we have more time for discussions. Yeah, it will be maybe interesting. Please, let's start.
Right. Thank you, everybody who is here, and for the opportunity to present here. I'm going to present you mostly the natural language interface of a scalable platform for maritime services on behalf of Metis. First of all, who Metis is. Metis is a Greek company belonging to Olympia Group, trying and achieving, actually, to apply the technologies of the 4th industrial revolution in maritime so as to assure cheaper, faster, and more environment-friendly transportations of both products and people. When we were thinking to apply the digital solutions, we have to face a dilemma of whether both the employers and the employees of the maritime will face our system with some skepticism concerning the complexity, as many of them see it not as a solution, really, but as an incrementation factor of complexity. That's why we followed a totally different approach, building the first cyber assistant dedicated to maritime. Our basic concept is that everyone in a maritime, in a company, in a shipping company, from the ship owner to the on and offshore personnel, have a personal assistant so that she can ask and learn information about her ships. Of course, the design of our system is of increased complexity and intelligence, involving both hardware that is installed upon the vessel and that store measurements in a database where our software agents have access in order to process the data and proceed to useful interpretations. But all this complexity is not seen by the user. All a user sees is a chatbot and let's say a Skype or a Microsoft Teams contact or even a mail contact where one can ask a question in natural language and this request is processed and a response is created by our software agents. So it is a personal assistant with no human interference at all. So this work is mostly about the natural language system, so I'm going to analyze it further. This is our main pipeline. This is what the user can see. They see a contact on various communication channels where they can send their messages. The message is first simplified and reprocessed and parsed in order to be classified into multiple categories. These categories represent the software agents that are the most suitable to further analyze the request. And they employ more spatial parsers in order to extract all the necessary parameters from the message in order to finally execute the task and return the response to the user. So, how did we implement this? The easy part, that was the integration with the various communication channels, was done using the Microsoft Bot framework. The rest of the processing was developed by us and was developed in Python. So, the first thing that takes place when a message is sent to our system is message simplification. We have implemented a custom spelling correction system, integrating multiple algorithms, and we also handle jargon of Maritime, mostly using an abbreviation list of Maritime collected by experts of the field. Then, it's necessary that the message is being split into sentences that have no conjunctions. This takes place in order to avoid redundant information when the parsing takes place. And this is achieved using SpaceA library, that is a deep neural network library that provides many functions for parsing or creating dependency trees like this and all. Then the first level of parsing takes place. In this stage, we extract vessel, user, and channel names from a message. For example, in this message, the vessel name is this, Star Libra. And we want this information not only to further process a message and return a response, but also to block requests from users who do not have privileges for all vessel or all users. Also, data extraction takes place in this stage, and we can handle various data formats, as can seen from these examples that are real from our systems. So, after all this processing and parsing, we want to classify a message in order to find the agents that are responsible for its execution. In order to be classified, a message must be first converted into a vector. So we further pre-process it so as to reduce the vector space, and we transform it to vector with a TF-IDF schema. Although we could use another approach like word-to-vec, for example, we benefit from this schema because of the size of our data set that was mostly collected from real messages and, again, experts of the field. So, after the preprocessing and the vectorization, our model is classified and by 3 classifiers that are combined. We have trained 2 strong classifiers, an SVM and a random forest, that consider all the preprocessing that can be done. They are trained in order to generalize well. But we have also trained a weak random forest model that does not take into consideration the removing of the stop words. This is weak because although it can overfit the training set, it does not generalize well. But we benefit from the weak classifier when we receive messages that have at most one word that is not a stop word. So in these cases, the stop words, in fact, improve the classification result, take advantage of the overfitting. Of course, in a more general case, the two strong models are applied. So, after a message is classified, the responsible agents for its execution start to further analyze the message in order to collect any useful information for the execution itself. For example, let's see this message that is classified as a request for the period export agent that wants to get a quantity and basically measurements of a quantity from our database and return a result. So we can see that this agent demands some basic parameters, and all this information is included in the message. But the message is always in natural language, so we cannot expect its form prior to parsing. That's why we built several parsers specifically for this task. Now let's see some more detail on this. This is an overview of our conjunction splitting algorithm. I included it here because it also involves a basic procedure that is subtree generation. How this is done? We first generate a dependency tree where we can see the syntactical relationships. So this is a conjunction between the main verb tell and the main verb send, and the conjunction term is simply end. So if we take as a root each of these main verbs and generate the subtree under these terms, of course omitting the conjunction, then we should take a subtree like this and a subtree like this. If we further split upon the conjunctions of the main verbs, of the main nouns, we will split also the position and the speed. So we would have something like, tell me the speed of vessel name N, or vessel name 1, sorry, and tell me the position of vessel name 2. But notice here that there is a them. Them is related to this main verb with a direct object relationship. So, because this is also a direct object relationship, we can infer that them refers to these three. So, if we transferred also these three here, after all the split, we take 4 independent subtrees where no conjunction is actually included.
Can I ask you right here?
Yeah, of course.
Okay.
Shouldn't be the speed and the position, those two bubbles on the same level, joined by and? Because now telling me the speed, the position, it goes once.
Yes. I see what you mean. The relationship is the same as here. It's a conjunction term and a conjunction. So it's simply practical that we did not draw it the same to Schwarz. You mean that position should be here, right?
Yeah.
Yes, it's simply practical and a matter of space, actually. Such as that send could be slightly higher, perhaps, but yes, it's practically the same relationship exactly. And conjunction. So, another important factor is our ability to detect quantities. Let's say, I'll show an example in our messages. So, let's see here. The user requested maximum shaft speed and shaft power. But how are these quantity names are stored in our database? Okay, thanks. Yes. We can see that the system returns a response for vessel propeller shaft mechanical power. This is about shaft power. And vessel propeller shaft rotational speed. This is about shaft speed and maximum value, of course. So, how can we infer that shaft speed and vessel propeller shaft rotational speed are the same when multiple of the words are omitted or their order is not known? This problem actually can be formulated by considering that a quantity is a set of n words and the message is a sequence of L words. Now, we cannot expect that the order of the words of the quantity will be respected, but we also know that this, the order of words in a message must be respected. So, first, we compute the similarity between the words of each quantity and every word in a message. Then, we slide this group of n words upon the L words and checking every neighborhood. In every neighborhood, we have first to associate the words of Q with words of its neighborhood. So, the word I is associated with the word of the message in this neighborhood that has the most similarity, of course. Then, the total detection score in this neighborhood for this quantity is computed as a weighted mean upon these scores. These weights were initialized by experts, but as our system being used daily, they are also learned. And lastly, another difficult task for our system is that it has to decide whether a request demands that we fetch or store information. Usually, this answer cannot be given using just content. So we combine a syntax and content-based classifier that first checks if a message is in a interrogative form. However, this is not always sufficient, as it may concern a formal question or about to store information and not fetch. Then, another feature is to transform this question to imperative form. And we check the main verb. Of course, a formal question like, could you tell me what's the value of? Now would be tell me. That tell is a feature that we want to fetch some information, for example. Then, another thing that is important is if we transform a question or generally a sentence into declarative form, which should be the subject. It's really different that a request says, tell me the speed, and I tell you that the speed is of this value. It's totally different. So, combining all these informations and searching for open relative clauses, that is, perhaps, could you please tell me what is the speed of the vessel? Then, what is the speed is an open clause to the main verb tell. So we have to analyze these clauses too. We have trained a model using this information to address this challenge. But how all this work? How well all this work, actually? So, the basic content classifier can achieve over 90% on validation sets. Note that this is when we combine all our models together. The strongest model of the three is the SVM model, and alone it can achieve about 80%, while random forest can achieve about 70%. But we noted that they are a bit complementary in what each of the two could recognize. So, in order to take a more accurate result, we combined the output of the two, and we trained both of them, maximizing precision in order to avoid false positives when a combination takes place. Then, regarding the interpretation of the task type, that was actually the previous slide. We tested on a public corpus of this that contained 3,372 sentences, and we were able to achieve 95% accuracy in this dataset. We do not have a dataset actually for every parameter we can extract, but we collected a dataset of 300 date formats where we are able to correctly detect and interpret about 73.7%. Lastly, considering the effectiveness of our system, we see throughout this presentation that expert knowledge is actually employed during the whole pipeline. Next, we shall evaluate the system's efficiency. The system efficiency concerns its robustness against noisy inputs and unexpected requests. As we already have seen, our system is pretty robust because domain-specific message preprocessing is taking place. So after this preprocessing, we have simplified and we have simplified the message in a way that we can actually expect a robust format, so as to classify it with the models we saw and parse it. And considering user satisfaction, actually this is a pretty subjective factor of evaluation. But in fact, we know that our chatbot is user-friendly and pleasant. It sure respects privacy and personality, and it does not allow requests for vessels that the user have no privilege. And regarding its accessibility, it can answer back quickly, encouraging the continuation of the conversation. Of course, we can never be satisfied with what we have achieved so far. So yeah, we have some more future work to propose and in fact do. We are working on most of these subjects. We mostly saw that our classifiers are coded based, but in fact a message is much more like this. So we would like to be able to detect if a message regards a request for past formation or a future prediction. This is not always easy using only the content of a message, but we could extract the dates and use them in the classification. Then, of course, the dependency tree we saw previously was in a standard format that we could actually predict and handle, but that's not always the case. Even in deep neural networks, sometimes do not parse a difficult structure so sufficiently. We would like to model this parsing difficulties, perhaps with a classifier in this stage, another classifier. And then we would like to personalize the classifier of his user. Actually, some users tend to ask certain messages and expect a slightly different output than others do. Although a generic language system should not handle this, humans in fact do. And they can understand, based on the other's context, what they mean. So to handle ambiguities in such messages, it is important to collect statistics and personalize the classifier. Lastly, we saw that we achieved 73.7% on date detection. That's okay, but we could improve it, of course, and actually handle even more difficult events that would demand not only the linguistic ability to parse them, but also connection with the database and prior knowledge, such as 2 days after the vessel's departure from port. Okay, when was the departure from port? But even if we know when was the departure from port, to associate 2 days after and the vessel departure from port is linguistically challenging. All right, so that's all. Thank you.
Thank you very much for the presentation. Please, do you have any questions? Yes.
To improve the accuracy of the system, have you considered using somewhat structured or controlled language to communicate with the system?
Okay, that was not arranged from the start, actually, because there are many platforms that depend on structured language or web interfaces, but you know, we wanted to rely on natural language processing because for us, natural language is not actually a fancy interface. It was our ultimate purpose. It was from the beginning of the project, we wanted that the user does not have to learn a new technology or even find himself coping with difficult language, even jargon.
Basically, you may have a smart assistant which guide the user to and easily adopt him to use somewhat structured, more structured.
Yes, I see what you mean.
Of asking questions and then just I was wondering.
Yes.
Because the precision would increase, I think, if you would take that.
That's for sure, but that's a bit lack of artificial intelligence, somewhat. Okay,
Right now we are very happy with the precision that we already succeeded. We have hundreds of users that they are using the system. Of course, the user after a while he adapts to the way that he asks questions. Okay, but it is very important not to give to him, try to learn to him another language to talk. Okay, like talking to his colleague, he has to talk to the system.
Also, we consider feedback, of course.
Yeah.
We see in practice its result, and then when a user says, "Okay, I asked this, and this is ridiculous. I don't get the response."
You have like feedback loops to improve on.
Yes.
Also, the bot try to start a conversation. If, for example, you ask something and there is a missing parameter there. Let's say that I ask, give me the position yesterday. Okay, of which vessel? So the bot will come back with the question. Please tell me which vessel you are referring about. So it is, yes, we try to give the feeling to the user that you are talking to a person, not to a machine. And this is, I believe that this is the future for any technology.
And my other question is whether you use some kind of, vocabulary of terms for your maritime
Jargon.
Jargon,
of course.
This is the
find
abbreviation.
similarities and so on.
Of course, yes.
This was the first step that Nikos presented there. It is the abbreviation. For example, in Maritime, they are using language like ETA, which means estimated time of arrival or such type of words. So the system must recognize that and understand that.
Yeah, and abbreviations is one thing, and another thing is synonyms and etc. So when a user asks something and you
Yes, I omitted from the presentation because it would take too long, but yes, we handle this.
Yeah.
Yes. If you want also more information, you can read the paper in the proceedings, and why not ask me whatever you want? Yes?
Next question, please.
Thank you for the presentation. Currently, there is also a lot of research on emotional elements, components. Did you regard that?
Yes, you are totally right. This is in our roadmap, even to change actually not the reply to the questions, not be always the same. Okay, try to give a personality to our system. This is in our roadmap, but we don't have implemented yet, but we have in our mind to do it in later stage.
Yes, this is actually version 1, maybe 1.1, but yes, it was a task-oriented chatbot, and we cannot expect it to completely pass the Turing test or completely understand your sentiments. Okay, it should, for this point, it would just answer you back correctly, and of course, we are improving on it.
Actually, the key here was that in order to reduce the complexity, because someone could ask a lot of different questions, okay? So in order to reduce the complexity of the problem was the idea to split the classifier, and from the agents and the parsing of the message to extract the parameters that you need to run a task. So the first step is to understand where you should address this message, to which agent, and then the agent must be parsed the message and extract for the specific service the specific parameters that he needs to run it. So by splitting this, we reduce a lot the complexity of the problem.
Design.
Yeah. It is like yesterday, it was very interesting during the second keynote speech that I don't know if I remember the name of the professor, but he mentioned about you should find the capabilities of a system in order to send the request to a system, if it is capable to respond to this. This is exactly the same, okay? You must find out which agent is capable to answer to this message.
Yeah, of course, it's getting much more complex if you try to implement also emotional information and data. And probably in the maritime service, emotions are not as important as in other sectors, like in industry, hotline, etc.
Yes, of course. If you try to scale this approach to other sections, of course you have to change some things. Yes.
And you also mentioned that you have like two functions to fetch and store, right?
No, there are only two actually, but
but basically just let's talk about those two. So your accuracy for a function of fetch is like okay, but how do you deal with this kind of accuracy?
fetch versus store.
If you want to store, because it's more critical, I think.
Yes, yes.
To store something in the database rather than.
Yes, there is always a confirmation that when you ask something, you say, for example, the wind speed now is tempo force. Okay, this means that he must take this as an information that must be stored in the database. So he will came back and, do you mean, actually, do you want me to set true wind speed equal to tempo force? So,
Yes.
yeah. So you must confirm that. Also, when we store the database, this is another key. Okay, what is the unique ID that you give to your parameters? The unique IDs that you give to the parameters must have itself not only what you are talking about. I'm talking about the width, okay, but what was the source of that? Okay, it was, for example, it is what captain said. So it is an input for the captain, it is an input for a weather provider, it is an input from the anemometer of the vessel. So this information is also stored.
Yes,
in the data.
and logistically, we evaluated this approach actually on this dataset. Yes, maybe you're not aware of this dataset. There are actually 3,000 sentences that are general questions or not questions. Actually, our task is not to detect if a sentence is a question or not, but this goes beyond this. Our system does correctly identifies if a sentence is a question, but what we measure here, and luckily they have annotations for this, is if it is in fact an interrogative sentence. So if the user actually asks for something, or it is a formal way to express something but not asking for. Such as in our system, it is common to say, could I please set this to, like I said earlier. Yes.
Thank you very much. One short question from my side, if I can. You said that about 100 workers, people use this system in this moment, but from my side, what kind of decision are you taken on the basis of this communication system? I think what of critical decisions, because if we spoke that accuracy of the system is 90%.
The accuracy
Yes.
To understand.
Yes. This is totally different than the accuracy of the data and the analysis. Okay.
Okay, and in my question is, what is the probability that the system give a wrong answer?
We must define not wrong answer, give the answer that I'm not expecting.
Yeah.
Because if we are talking about wrong answer, then we are talking about the analysis of data.
Not wrong answer, but on the basis of this answer, I undertake the wrong decision. In this one, it is possible or not?
It is not possible to take a wrong decision if someone does not give you the answer that we are expecting to have. Okay. If I give you wrong data.
Okay.
Or,
it's clear.
But this is totally different discussion than this one. Okay.
Okay.
Yes.
But it is not so critical if the system does not give me, let's say that I am requesting what is the weather condition and it sends me the analysis of the wind effect on the vessel. So it's not so critical, I have to request it again in another way. Okay.
And I have to
but if,
train the
for
model
example, I
guide.
want the weather and yesterday and it will be provide me not the weather but something, the weather but it is not accurate.
Yeah.
Okay, the information that gives me to me, because this is important.
Yeah.
But this is a matter of the analysis of the data behind the cloud. Okay.
Yes, we just focus on the natural language here.
Yeah.
Okay, very good, very interesting. Thank you very much for the presentation.
Thank you.
And I have certificates. For Serafeim, sorry, for Nikolaos, 2 certificates. Who is who?
Both of us.
Thank you. Thank you very much. Thank you very much. And the next presentation is my presentation. One moment, please. I'd like to present some short presentation about the knowledge acquisition user computer simulation of manufacturing systems for preventive maintenance. I said it, I come from University of Janagura and I work in Faculty of Mechanical Engineering, and I deal some years with maintenance of manufacturing system, production systems, and this presentation, this concept is related to the concept of Industry 4.0, because the preventive maintenance, predictive maintenance are very important for the future of technical systems overall. Of course, very important question and very important thing is to implement the intelligence or the implement of procedures that can interactive react on the failure in the manufacturing systems. The massive customization production, it is the very challenge for the future, and the system should be the manufacturing system should have the possibility, for example, for self-organization, or to change the organization if something is wrong in the manufacturing resources. What is the preventive maintenance? System includes the systematic inspection, detection, and correction of inspection failures ever before they occur or before they develop into major effects. It means if we have a manufacturing system, we can foresee what's happened or we know what we should, the system know what the system should make if something is wrong. That's all. The research problem, again, is a simulation model of discrete manufacturing systems. We deal with discrete manufacturing system, automotive, for example, and so on. The problem is how to develop the knowledge database based on the analysis of simulation experiments of predictive maintenance. The building of knowledge database is very important, and it is refers for example, in Poland we have a lot of problem with personnel, and in maintenance area work a lot of old and very workers with great experience, and the problem is how we can take this experience and how we can build the knowledge database on the basis of the experience of these people. But it is different problem for this presentation. Here we try to use the simulation methods to build the knowledge database and to analyze some scenarios of for the behavior of manufacturing systems. We propose a methodology for the acquisition of knowledge for preventive maintenance. We have requirements, design, implementation, and verification of the process. First, we try to define the main objectives of preventive maintenance for individual manufacturing system, building simulation models of the system, design the simulation experiment, conducting the simulation experiments, and transferring the results to the research as a knowledge, as rules, and analysis of the results, and verification. If the knowledge is valuable, we can update the knowledge database and we can repeat this process without of. I think this process can be repeated every month, and if something is changed in the manufacturing system, we updated the knowledge about the system. A very simple example. We use as a tool Technomatics plant simulation system. This system simulation system software for Siemens, and you can see here the structure of the system. It is we have here machines, manufacturing resources. We assumed that this system is automatically, but here you can see the workplaces for the service. It means it is not the normal worker, not the service worker. It means if this machine is failure, here we have place for the service, and somebody should come and repair this machine, or and here we have intermediate buffers. We assumed that the operation times are changed on the base of the log normal distribution, and at the same we have assumed for the setup times for the systems. Here, and you can see here with this operation and setup times for the machines. Whereas operation times are the same, the setup times are the same too. We produce in this system 4 products, and you can see the sequence of batches: 100 parts A, 300 parts B, and so on and so on. For this model, we prepared a set of experiments, 24 experiments, where we can see here the buffer capacities. For example, here buffer 1, the capacity is 1, or here buffer 3 is the capacity is 5, and you can see here the different availability of the manufacturing resources. The availability is changed from 70 to 90%. It is, of course, if the availability of the manufacturing resources are lower, we have more and more failures of the system, and we need more effort of maintenance workers. And you can see here the results of the simulation experiments. It is an example for free maintenance worker, for example. It means for this system we have free maintenance workers, and you can see how it's changed for the different capacity of and different availability of manufacturers. How it's changed the throughput of the system and how it's changed the average lifespan. This average lifespan is, we can compare it in work in progress. It means this factor shows us how long a product stays in the system. For example, it's changed from 30 to 55 minutes the product can stay in the system. Okay. You can see what's happened with the throughput of the system for 1 worker, 2 workers, 3 workers, and 4 workers. It means, of course, if we have 4 workers, more is not necessary, because if you have 4 maintenance workers, every failure in the system can be the machine can be repaired suddenly, yeah. And you can see we have here for different experiments, but different level of throughput of the system. Of course, for maintenance workers, we have the best throughput, but of course the highest costs, because we need 4 workers for the system. For 1, you can see it here. You can see how it's changed the lifespan of a product for the different number of maintenance workers here. And you can see that for 1 worker we have the worst work in progress. The products stay longest time in the manufacturing systems. On the basis of the simulation experiments, we can collect the new knowledge about the number of maintenance workers impacts, how the number of maintenance workers impacts on the system throughput, proportional. For the system with 3 resources, the maximum number of maintenance workers is 4. The average life has, this is assumptions. The average lifespan of the products for the number of maintenance workers is greater than 2, and does not change proportionally. In the next step, we have changed the topology of the system. It means not exactly topology. We change the dispatching rules on the machines and buffers. It means in the first version here, we can send the product from here only to this buffer. In this one, we have changed it. It means this machine can send part to this buffer or to this buffer. Or this machine can set it to this, or to this. From the technology side, the technology order of the production is not changed. It is the parallel serial manufacturing system. It means it is no different for us if the product will be produced in the following sequence: this machine, this buffer, or this machine, or this machine, this buffer, or this machine. Because these machines and these machines are responsible for the same technology. Yeah, it means these 3 machines realize the same technology operation, and these 3 machines realize the same technology operations. Okay. And we can compare the for the second model what's happened. We do not change the buffer capacity. We change only the topology. It means the organization of the material flow in the system. and it is interesting what's happened. We increase the throughput for a system. The lifetime is not changing very much, but we can compare that for one maintenance worker, we can increase the throughput of the system about more than or about 14% in the maximum here. For other configuration for 4 workers, it is about 4%. Yeah. It means on the base, it is example. If we analyze such cases for the individual, for special manufacturing system, we can build some knowledge about the system, and we can answer, okay, if you want to reach some factors, you need so and so number of manufacturing workers. And we can build the decision rules for this. For example, if a number of workers is, then if a number of workers, and so on and so on. Of course, we can build a lot of number of rules. If it is important or not, it is depend from the production manager, planning manager, and so on. And on the base of this set of course, good prepared simulation experiment, we can build the knowledge database about an individual and special manufacturing system and about the behavior of the manufacturing systems. Of course, it should be verified on the real, on the base of the real systems, but it is possible too. Yeah? And on the base of our experiences, the results are very, very interesting. From my side, that's all. Thank you very much for your attention, and maybe you have any questions.
So you're basically dealing with the optimization task, system and resource optimization.
Sub-optimization. It is the problems are NP hard, and it is the buffer allocation problem. It is well-known problem, yeah, and it is NP hard problem. And but we cannot. We looking for the available solution, not for the best solution. It means optimization is very, very difficult in this kind of systems. Yeah, it is.
So did you find or not the optimal solution for this experimental system? Let's say, what is the optimal number of workers and the topology for the experimental system?
No, but it is not interesting for us. It is interesting for us is answering for the question, for example, yeah? For the manager, for the production manager. You have 2 maintenance workers, yeah? For this system, or if you want to dedicate 2 maintenance workers for the system, you can reach, this is good. One moment. For this topology, for example, you can reach for 2 maximum this throughput of the system. And it is simple answer. With the optimization in production processes, it is not necessary. But very important for automotive, for example. Of course, it is not necessary. No, it is not possible. Okay. Sorry. It is. I think it is not possible. But for the production manager for automotive, is very important to answer. Okay, what can I get for these resources and for this personnel, for example? What is the? It is the kind of sub-optimization, because you can see, okay, maximum is here.
But if you have 2 workers, for example, okay, so the goal of that manager should be what is the optimal topology of the system that would cover those 2 workers,
yeah,
for the maximal output or whatever.
one here, is only 24 experiments. Yeah, the number of combinations, the explosion of combinations is so big that it's not possible. Normally, it's an NP-hard problem. It is not possible to find the best result for this configuration and so on. And we try to answer, okay,
The best possible.
it is possible, but we need some thousands of years, yeah, maybe to answer the question, yeah. Okay, we can use tabu search algorithms or other to find or other heuristics, yeah, to find the solution, optimal solution. But it is not the goal of our work. Yeah? We try to give some subsystem, yeah, that can answer on the base of this experiments. Okay, you can get this on this. Of course, you can optimize the production in real, but from my experience and my team experience, it costs a lot of money. And with simulation tools, you can do it very fast. You can prepare some real scenarios, and you get answers. Yeah. If you want to simulate it in real production, of course, and model the system in reality, it costs a lot of money, and nobody have a time for this. Yeah. Maybe some question more. Yeah.
Okay, I have a couple of points that I would like to mention. First of all, you mentioned about the predictive maintenance at the beginning. This is not actually predictive maintenance here. Here is sustainability of a production system. Predictive maintenance means that I'm trying to apply new techniques of monitoring on the machines, of the production machines, and estimate the remaining usable life of them. Okay.
Okay, that's right. Okay, that's right. Okay.
This is not a problem of predictive maintenance here. The other one is that I cannot understand. Okay, you make different scenarios. Of course, in a real case, you have a lot of information for each machine to know what is the percentage of the availability of the machine. You don't have to create so many scenarios of various numbers. Also, I don't understand why you have to put in the buffer different numbers, because the buffers, the capacity of each buffer is well known. So
No. You can model the.
If you want to change the buffer,
yeah, you can,
because when you have a factory, you have a buffer.
But of course you can say, okay, because the buffer, it means the boxes, for example, in the production.
Yes.
And so I can say, okay, if I say in box, it should be only 5 parts, it will be so. Yeah, you understand it? Of course, the box could be greater, but we can implement it in the production. It means what should be, what is for us the most interesting, the buffer capacity. Of course, it is normal if the buffers are greater, yeah, the work in progress is greater, yeah, and it is not very good for production. The throughput could be better, but the work in progress is worse, yeah. And this factor could be modeled, this not, yeah. Of course, you are right. Normally, I can select only one row from this, because I know that this machine has only 70% availability, and so on and so on. But it is true that it is not only availability. In this factor, we can say about the availability of machines, but for example, for this availability is changed. Could be changed, for example, and it is depend from, for example, for tools. Yeah? And it could be changed, and we can assume that the availability of this machine can be changed from 70 to 75, for example, percent. Yeah? And this factor can be changed too. But it is independent from us. But this factor is dependent from us. Okay? More question? Please. Okay. Thank you very much. Okay, and the last presentation is for Mr. Eryk Szwarc and Irena Bach-Dąbrowska and Grzegorz Bocewicz, and it is competences management in teacher assignment planning. Let's start.
Thank you. Ladies and gentlemen, each year in each university the problem is how to assign teachers to courses, or opposite. Thus we have enough competency in our teacher staff to assign courses. Or can we can ask the reverse problem: if we doesn't have enough competences, what the structure of the competence will guarantee our assignment. So my motivation to research with this kind of problem is that each year before the course starts, we need to schedule courses, and before that do the teacher assignment. This is the most popular approach. We use this, a lot of friends of other universities use this approach. However, of course, this is not only one approach used in research. Also, other research is that before the teacher assignment, the schedule is done. In this approach, the main hardness is that it's really hard to assign teachers to given schedule in a weekly horizon, something like this. And the third approach, which we could find in the research, that the scheduling is doing simultaneously with teacher assignment. So the complexity of the third approach eliminates the research about this. We not include this. And the second approach also. So we focused only on the first approach, and about scheduling is a lot of research. In our university, we focused on the first stage of this approach, the teacher assignment. In teacher assignment, the main key criterion is the competences, the conditions guaranteeing admissible solution, because we didn't found any research about this type of conditions, and the robustness to disruptions due to the realization of teacher assignment. Of course, disruptions occurs, and we need to be robust. So let me formulate our problem. It's a simplified problem, really little scale of the problem, where we have 4 courses. In each course we have some groups. These circles or tokens is the one group for this course, 3 groups for this course, and so on. Of course, each group has some number of hours to teach. Of course, we have set of teachers to teach these courses. They have some competences. We propose binary table to define does some teacher has competence to teach course. The value of 1 means that has competences. 0, she doesn't have. So let me propose some graphical representation of this type of table by the links between the teachers and courses. Of course, these lines, these links, is the value 1. Of course, there are many of constraints to include. The main constraint is that teacher has some hour limits to teach. The minimum, the maximum, different countries has different teacher limits, of course. We focused only on this one. This is the main constraint in our problem. So, in the teacher assignment, expectation is that each group need 1 teacher, and each teacher need to realize assumed hour limits. Of course, we have capabilities given by the competence structure, and the question is, does there exist admissible solution, admissible assignment, which satisfies expectations by given capabilities? In this simplified example, we have 24 combinations of assigning groups to teachers. One of the scenario I show you on this screen. I distribute the groups to teachers, and of course, for these competences, this competence structure, answer is that there is a admissible solution. So, we see that the limits are satisfied, and of course, there are some cases when competence structure doesn't guarantee admissible assignment. For example, there is different competence structure, less competences, and in this case, one of the assignment is here, and we see that this teacher has not satisfied his limits of teacher hours. So we need to find some sufficient conditions for competence structure which guarantee admissible solution. Because of this is the NP hard problem. There is in large scale, for example, in our faculty, it's 50 teachers, 100 courses in each semester, and it's really, of course, big combinations, a lot of combinations to check, and of course, we need to know there is any admissible solution. So we propose 3 conditions. For the first condition, we need to check for each course. If A is less or equal than B, then assignment could exist. Where A is demanded course hours, this course demand is 9 groups multiplied by 30 hours, it's 270 hours to teach, and B value for this condition is the sum of the maximum limits of these teachers. The sum is 210. So we see that in this example, this condition is not fulfilled. The second condition is if C is greater or equal than D, then assignment could exist, where C is the number of possible hours to be assigned to a teacher. This teacher is linked to 2 courses with 1 group, each course has, and of course his C value for him is number of possible hours is 60, And D value is the demanded minimum hour limit for this teacher. Minimum hour is 90. Of course, in this example you can see that also this condition is not fulfilled. And the third condition is we need to check for each pair of teachers. For this example, we see 2 teachers, 1 course, and for this condition, E is the number of possible hours to assign to a pair of teachers. They are linked to the same course, which has 4 groups multiplied by the number of hours. We have this result, and the F value is the sum of demanded minimum hours of this pair of teachers. Of course, also this is the example where 3 conditions are not fulfilled. To be sure that any admissible solution exists for our competence structure, all conditions should be satisfied. So for our previously presented competence structure, we can check each condition. For the first condition, the results of calculation is presented here, and the green color means that everything is okay for this condition. The second condition, we can see calculations here, also is good. And the third condition, we can see one result on the red color, which means that this condition is not fulfilled. So it proves that the previously presented one of the 24 cases, and all 24 cases are not they are not admissible solution. So we state another question: does there exist a competence structure that guarantees admissible solution? So there's some kind of reverse problem. Of course, there are many possibilities to competence at the yellow links show it, and let me present the example when everyone add any competence. So the scenario is we can name it the full structure of competence, and we can check, does this competence structure guarantee admissible assignment? Of course, we don't need to check all of combinations. Of course, we can check only these 3 conditions, and for this example, of course, 3 conditions will be fulfilled. So we know that if competence structure will be full, there will be any admissible solution. You can ask maybe some other not full competence structure also admissible. Of course, this open question. Our conditions don't give answer about this type of question, only for the does there exist for the assumed structure of competence. The proof only for the full competence structure that assignment exists. Now its limits are okay. So conclusion of this part of presentation is that our sufficient condition gives answer: does a competence structure guarantee admissible assignment? Other two other competence structures which are for which is admissible solution can we find, and our conditions could be used in the area of robustness of the competence structure. There is a gap in the literature about it. We didn't find about the considerations about the robustness. So, for example, we have last year, of course, it is common example of robustness when during the academic year teacher is absent and someone should fulfill this gap and to teach the last hours of courses which was assigned to the absent teacher. Of course, there is a question: does a given competence structure which we have is robust to absence of one teacher? So, for this type of absence, we need to check 4 scenarios of absence of one teacher, and we can check all conditions for scenario when this teacher will be absent, this teacher will be absent, and so on. And we can see that in the one of this scenario, one of the condition is not fulfilled. I don't show all of our conditions because it will be a lot of numbers here. Only I focused on the condition which is not fulfilled. For our 4 scenarios, only 3 guarantee the teacher assignment. So intuition for this type of calculation is that we can use measure of robustness to the absence of any number of teacher. It's a simple formula where on the up of this formula is number of scenarios for when solution is admissible, and on the down value is the number of all possible scenarios of teacher absence. So for our example previously shown that for absence for one teacher we have value of 0.75, which means only that 3 scenarios of 4 possible scenarios will be okay, and 1 only is not. Of course, there is an open question that does there exist a competence structure that guarantees robustness by value 1? So if any one teacher will be absent, it will be okay. It's part of other considerations in other papers. So I only conclude my presentation. So we focused only on the teacher assignment. We proposed a model with sufficient conditions and a model of robustness only for the one type of disruption. Our future work will be the development of the method for the robustness assessment for some alternative competence structures. And of course, these methods we try to implement in some of decision support system, because there is also a gap in our Polish commercial systems for the universities. They don't have this type of decision support making. So thank you for the attention.
Thank you very much. Let's start with the questions. Nobody have a problem with planning? With estimates?
I think it's a well-known problem for anyone.
Maybe I'll ask. Well, from our point of view, look, it's very interesting solution. It's quite simplified, because there are a lot of other obstacles and conditions.
Yeah.
But I just like to ask, I see that you do not have yet production version of the system, but maybe you tried to see what it would look like if you would try to make the schedule of the whole faculty or university. How much time it would take,
Yeah.
and how feasible the solution would like.
It's the we didn't do any calculations on the real size of the problem which we have all on our faculty. As I said, 50 teachers and 100 of courses. I tried some calculations in Groby language and linked with the MATLAB, and it was I tried to remember the size of the problem. It was some kind of 15 teachers and 30 courses. Sorry, I don't remember the time of computation. However, we found the results of some our calculations. We try to our next step will be to test these models implemented in some software and try to find the scale which we can handle with of this type of problems. Of course, there is a lot of other conditions needed, other constraints. It's only need to formulate them, because we try to. Our idea is to use the constraint programming, so we only focus on the constraints and modeling. Thank you.
Thank you very much. Any questions? Not? Okay, thank you very much for an interesting presentation. Okay, that's all. Thank you very much for your activity in this session, for discussion, questions, and thank you.
And thank you, Sławomir, for saving the day.
Thank you. Thank you very much.
Send my best wishes to you.
Yeah, of course.
Thank you.
Thank you. Okay, let's go to coffee break. For lunch. For lunch.